Hello students, welcome to EDAMIGO. I am Siddharth Sabarwal, Rank 3 Engineering Services 2015, and this is day 2, and I have posted 3 questions on digital electronics, and the topic was Boolean algebra, and I'm providing you the video solution of the 3 questions. And in these 3 questions, the first question was on the concept of prime implicants. So with the help of this question, I will be providing you the concept of and explaining you the concept of prime implicants and essential prime implicants. Okay. So I will be telling you the concept of essential prime implicants and prime implicants. Okay. Now the function is given to us. Okay. The first function is f. The first function is f 0, 2, 4, 5, 6, 7, 8, 10, 13 and 15. Okay, so I will be drawing the k map of 4 variables w, x, y and z. Okay, okay, so this is 0, 1, 2, sorry, this is 3, 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10, 12, 13, 15 and 14. Okay, now I'll mark all the terms. So 0 is there, 2 is there, 4 is there, 5 is there, 6 is there, 7 is there, 8, 10, 13 and 15. Okay, so this is the k map of the function f. Okay, now let me draw the terms which all the implicants. Let me tell you what is the prime implicant, meaning of prime implicant. Okay, so now let me write the definition of prime implicant. Okay, so prime implicant means a prime implicant is a product term obtained by combining the maximum possible number of adjacent squares in a k-map. Okay, okay, so this is the k-map. So let me copy this k-map, then I will be able to explain you this prime implicant meaning much better format. So okay, okay, so this is the k-map. Now there are these are the ones. Okay, so I will be marking the squares which we can get. Okay, so by combining these ones we can get a term, that is, here we have w bar x bar, w bar x, wx and w x bar. Here we have yz, y bar, sorry, y bar z bar, y bar z, yz and yz bar. Okay, so in this term, these are the maximum possible number of the squares, adjacent squares we can combine. Okay, so we will get a term that is equals to w bar x. Okay, so this is one prime implicant of the K-map. Okay, so this is okay. So we have already covered these ones. Okay, so now let me look at the another term, that is by combining the squares which are at the ends. Okay, so this is w bar x bar, w bar x, wx, and wx bar, y bar z bar, y bar z, yz, and yz bar. Okay, so if we combine these terms, we can see that in these terms, so in these squares, in these four squares, the terms which are common, which are not changing, so we can see that in these squares the terms which are not changing is x bar is not changing because w is changing. Okay, here it is w bar, here it is w, so w is changing, x is not changing, x bar is not changing, so x bar is a term. Similarly, we can see that y bar is changing because here it is y bar and here it is y, so y is changing term, but z bar is not changing. So by combining these four ones, we will get x bar, z bar, the another prime implicant. Okay, okay, now if I combine these four ones, then so this is w bar x bar, w bar x, wx, wx bar, y bar z bar, y bar z, yz, and yz bar. Okay, so by combining these, we can see that in these four squares, the term which are common, which are constant, which are not changing, we can see that z is not changing here, so z is a term, and we can see that x is not changing, so xz, this is a third prime implicant. Okay, now there is one more term which we can get is by combining these four ones. Okay, so this is another prime implicant which we can get. So w bar x bar, w bar x, y bar z bar, and the last one is y z bar. So we can see that in these four terms, w bar is not changing and z bar is not changing. So the prime implicant here is w bar z bar. So this is the fourth prime implicant. Okay, so now we can see that only in the four ways, there are only four ways in which these ones can be combined together. So that is, there are only four number of the prime implicants available. Okay, okay, now you can have a doubt that we can have this also a prime implicant, okay, by combining these two ones together, but this is not a prime implicant because in the definition itself, a prime implicant means that the maximum possible number of the adjacent squares in the K-map have to be combined together to form a prime implicant. Okay, so these are the four ways in which we can combine together. Now as we know that while defining a function f, we need to combine only those prime implicants, or we need to add only those prime implicants which are able to cover all the number of ones which are in the K-map. Okay, so for example, in the same example, if we take this is the function 1. Okay, so this was the function. So this was one prime implicant as we have seen, this was another prime implicant as we have seen, and this was another prime implicant as we have seen. Okay, so this will give me w bar x, this will give me these four squares at the corners will give me x bar z bar, and this will give me x z. So my function f is equal to w bar x plus xz plus x bar z bar. Okay, the same function f can also be written as, 1 1 1 1. Okay, so I can combine these in another method also. So these four are there. The another one is this, and the third one is this. Okay, so we can see that these four at the corners will give me x bar z bar. This at the center will give me xz, and these the pink one or this one, the corner 2 and the this corner 2 ones will give me the term that is w bar z bar. So the function f can also be written as xz plus x bar z bar plus w bar z bar. So in these two formats we can write the function f. Okay, now this is the maximum possible number of ways in which this function can be written. Only two possible ways are there. Now this, I have shown you the meaning of prime implicant. Now let me tell you. So there are four prime implicants here. Okay, four prime implicants. Now let me tell you what is the meaning of essential prime implicant. Essential prime implicant. What is the meaning of essential prime implicant? So the definition of essential prime implicant is that, so the definition is, if a prime implicant exclusively covers a min term, then that prime implicant is essential prime implicant. Okay, so let me explain you this with the help of the particular example as we have seen here. Okay, so in the function f, we have these min terms available. Okay, so there were actually how many min terms? 1 2 3 4 5 6 7 8 9 10. There were 10 min terms in function f. Okay, and we have seen that these 10 min terms are covered by four prime implicants. This is 1, this is 2, this is 3, and this is 4. Okay, now this is the first prime first prime implicant, this is the second prime implicant, the third prime implicant, and the fourth prime implicant. Now if we look at this first min term, then this first min term is covered by the second prime implicant and the fourth prime implicant. So this is not exclusive. Okay, the if we talk about this min term, is covered by second as well as fourth, so this is also not exclusive. This min term is covered by the first prime implicant and the fourth prime implicant. This is covered by the first prime implicant and the second prime implicant, and the third prime implicant. This is covered by the first prime implicant and the third prime implicant. This is covered by the first prime implicant and the fourth prime implicant. This 13 is covered by only third prime implicant. So 13 is covered by only the third prime implicant. Similarly, 15 is covered by only the third prime implicant. Okay. Similarly, if you look at 8, so 8 is covered by only the second prime implicant, and similarly 10 is covered by only the second prime implicant. Okay, so the third prime implicant is exclusively covering 13 and 15. Second prime implicant is exclusively covering the 10 and 8. Okay, so these are the prime implicants which are exclusively covering a min term. So here we can say that second and third are essential prime implicants. Okay, so let me explain you once again. So we started with marking the k-map of the function f. Then we try to find out the prime implicants available, and how to find the prime implicant by marking or combining the maximum possible number of the adjacent square in the k-map. Okay, we got four prime implicants. Now out of these four, we try to find out which of the prime implicants are exclusively covering a min term. Okay, so we found that third is exclusively covering 13 and 15, so third is the prime implicant. Second is exclusively covering 10 and 8, so it's an essential prime implicant. So such kind of question can be asked in any of the competitive exam. It's very important. Four prime implicants are there and there are two essential prime implicants. Okay, so this is the part one of the question number one. Okay, so let me do the another one. Okay, so this is another question. Okay, so we will do this. Zero 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 1 0 1 3 2 4 5 7 6. Okay, so let me mark all the ones are here. So 0 is there, 2 is there, 3 is there, 5 7 8 10 11 14 and 15. Okay, so there's a less space there. C bar, D bar, C bar, D, C D, and C D bar. Okay, now C D, C bar, D bar, C bar, D, C D, C D bar 1 0. Okay, so this is the function f, that is a b c d. Okay, now we have to find the prime implicants and the essential prime implicants. So first of all, we will mark the possible number of prime implicants there. Okay, so the first one is this red, combining the all the squares at the corners. Okay, so we can see that in these squares, which one is common? So b bar is common, we can see, and d bar is common, so it is b bar t bar, the red one. Okay, this is the first prime implicant. Okay, so the second color I will use orange. Okay, so this is the second one possible here. So this is the second one. So second one will give me C D. So this was first. Okay, now let me write the third one. So we can see that the third one is this, and third we can see that here A is constant, not changing, and C is not changing, so A C. Okay, now another term, let me change the color. So this is another term, the fourth one, because we cannot have the four adjacent squares, only two is the possible, so fourth one. So here we can see that A bar B is constant here, and D is also constant in these two squares, not changing. Okay, So these are the four prime implicants. Okay, so one more is also there. Let me write with black. These two squares at the bottom and the top. Okay, so this will give me the fifth one, which is common. B bar is constant and C is constant. So B bar C is the prime implicant. Now, to find out the essential prime implicants, we have to find out the min terms which are exclusively covered by only one prime implicant. Okay, so we can see that the min terms which are encircled by only one colored square, it is exclusive. Okay, so we can see that the zeroth min term is covered by only the red color square, so it is exclusive. It is covered by the first min term, first prime implicant, sorry, first prime implicant. Eighth is also exclusive, so it is also covered by the first prime implicant. So we can say that the first prime implicant is covering the two min terms exclusively, so it is essential prime implicant. Okay, now if we look at the min terms so let me change the color, let me use this. Okay, which are like 3, the third min term, the seventh min term, the 15th, and the 11th. All these are covered by more than one colored square. One is covered by orange and black, this is covered by blue and orange, this is covered by green and orange, this is covered by black, orange, and green. So these are non-essentials. Okay, they are not exclusive, sorry, these are not exclusive. Okay, so now this is also not exclusive, covered by black and red. Now if we look at the 14th one, this is covered by only green square, so that means the 14th one is exclusively covered by the third min term, the third prime implicant, sorry, the 14th min term is covered by third prime implicant, so it becomes essential prime implicant. Okay, similarly if we look at the fifth min term, it is exclusively covered by fourth prime implicant. Okay, so in this whole figure, whole K map, you can see that only 0th, 8th, 14th, and 5th, these are the four min terms which are exclusively covered by the prime implicants. So the prime implicants which are covering these min terms will become essential prime implicants. So 0 and 8th are covered by first, 14 is covered by third, so third become essential prime implicant, and fifth is covered by the fourth prime implicant. So first, third, and fourth become the essential prime implicant. So there are 3 essential prime implicants. Okay, 5 total prime implicants and 3 essential prime implicants. Okay, now let's look at another function. Here function f is equal to ABCD, that is equal to 2, 3, 4, 5, 6, 7, 9, 11, 12, and 13. Okay, so let me draw the K map first. A, B, C, D, C bar, D bar, C bar, D, C, D, C, D bar, A bar, B bar, A bar, B, A, B, A, B bar. 0, 1, 3, 2, 4, 5, 7, 6, 8, 9, 11, 10. Okay, so let me mark all these. So we can see 2 is there, 3 is there. Okay, so 2, 3 are there, 4 is there, 5, 6, 7, 9, 11, 12, 13. Okay, so let me mark the squares here. So this is the first one. So here we can see that it is a bar b. This is the second one. So here we can see that the constants are c is not changing here and a bar is not changing here. So the second one is a bar c. Okay, this is the third one. Third one is b is constant here and c bar. Okay, and the fourth one is, this is the fourth one. Okay, we cannot form the four adjacent square, we cannot find that, so only two will be, two adjacent square can combine. So it is a b bar and the constant here is d. We can see that. Okay, so thus we can see that there are four prime implicants. This is the fourth one, four prime implicants. And now if we want to find the essential ones, then we have to see the minterms which are exclusively covered by a particular square. So we can see that this is the third minterm is covered by the second prime implicant exclusively. The second minterm is also covered by the second prime implicant exclusively. So we can see that the second prime implicant is essential prime implicant. Okay, if we look at this ninth minterm and the 11th minterm, they are exclusively covered by the fourth prime implicant. So this is also essential prime implicant. The 12th and the 13th minterm are covered by the third prime implicant exclusively. So this is also essential prime implicant. Now if you look at the first prime implicant, it is covering 4, 5, 7 and 6. All these minterms are covered by other prime implicants also. So they are not exclusively covered by this first prime implicant. So this is non-essential prime implicant. So if we want to find, we can say that essential prime implicant, there are three essential prime implicant and there are four prime implicants possible here. Okay, so I have to add a page here. Okay, so let me write the another question, the last part of the question. W x y z is equal to summation 1 3 6 7 8 9 12 13 14 and 15. Okay, so let me draw the K map. wxyz 0001. Okay, so okay, so this is 1 1 6 7, then 8 9 12 13 14 and 15. Okay, so let us now combine these. So we can see that this is one square that we can form the first one. So here we can see that here x is common and here y is common. So we have xy, the first prime implicant. Okay, and we can see that this is the second one. So here we have w w x. Okay, this is the third one. Okay, so here we can see that y bar is not changing and here w is not changing, so we have w y bar. Okay, and this is the fourth one. Here we have w bar x bar, and in these two terms we have z as same, so w bar x bar z. So this is the fourth prime implicant, this is the second prime implicant. Okay, now if we want to find essential and non-essential, then we can see that these two min terms are exclusively covered by the fourth prime implicant, so this is essential prime implicant. Okay, similarly these two min terms are exclusively covered by the first prime implicant, these two min terms, so this is also essential prime implicant. These two min terms are exclusively covered by the third one, so this is also essential prime implicant. But we can see that the second one is covering the min terms which are non exclusive. Okay, they are covered by other prime implicants also, so this is non essential prime implicant. So we can see that there are four prime implicants and there are three essential prime implicants. Okay, so this is a solution to the first question. It's a very lengthy question, but I have tried to explain you in a best possible manner what are prime implicant and what are essential prime implicants. So the most expected question from this example is to find out the prime implicants and the number of essential prime implicants. That can be an expected question in GATE exam. Now this is the question. We have to draw the NAND logic of this function. Functions complement. Okay, okay, so first of all let's find out the function. Okay, okay, so this is 1 is there, 2 is there, 3 is there, 6 is there, 10, 11 and 14. Okay, so we can see that this is the first term which we'll get, this is the second term which we can get, and the third term by combining these four squares. Okay, so the first term will be a bar b bar, the second term will be c d bar, and the third term will be, so in these two we have b bar as common, and here we have c as common, so we have b bar c. Okay, so we have function f is equals to b bar c plus a bar b bar plus c d bar. Okay, this is the function, so we have to implement function bar, that is b bar c plus a bar b bar plus c d bar whole bar, that is b bar c whole bar multiplied by a bar b bar whole bar multiplied by c d bar whole bar. Okay, so since we have to implement this function complement, so assuming that the complements of the inputs are available, so we have b bar c, we will get b bar c complement a bar b, so we have a bar b complement c d bar, so we have c d bar complement. Apply this as input to the NAND gate, and then we have to apply a NAND gate again, because here we will get the product of these three terms with a complement, but this NAND gate will act as a NOT gate, and here we will get F complement as the result. Okay, so this will be the implementation. Okay, so this was a quite easy question, so I will try to keep more difficult questions in the later question series. So this is the next third question. So here it is given that we have to implement not more than two NOR gates. Okay, so this is the function f given to us. So first of all, let me draw the k map. There's a don't care condition also given to us. So this question will help you to understand how the don't care questions are solved. Okay, so now let me put the first of all the function f. So 2 is there, 4 is there, 10, 12, 14, and then there's the don't care condition also. 0 is don't care, 1 is don't care, 5 is don't care, and 8 is don't care. Now don't care can be used as 1 whenever it will help us to minimize the terms. Okay, so here as we can see that there is a two adjacent ones which are present, but since there are don't care conditions, so we can expand this to minimize the terms further and assume that these don't care as 1. Okay, so these don't care can be assumed as 1. So here we can see that the term will be c bar d bar, so this will give me c bar d bar. Similarly, these two ones will form a two adjacent squares, but since we can extend and use the don't care conditions, and we can extend these to a group of 4 squares, and this will give me a term. So here a is constant, and here we can see that d bar is constant, so a d bar. Okay, and the last term which we can get by combining the 4 terms at the corner of the k map. So with the help of don't care conditions we are able to do that. So here we can see that in these squares we have b bar as common, and here we can see that d bar is common. So here we can see that the function is c bar d bar, A d bar and B bar d bar. So it is C bar as, sorry, taking d bar as common, so C bar plus A plus B bar. Okay, so this is the function f. Function f can also be written as A plus this. Okay, okay, because we know the property, right, that x plus y conjugate is equals to x plus y complement is equals to x complement y complement. Okay, so using the same property we get this. Okay, now using two NOR gates we have to implement it. Okay, so if this is the input D, this input should be A bar C B bar, then the output will be D plus A bar C B bar whole bar or whole complement. Now since in the question it is given that complement as well as the original inputs are available, so we will use a NOR gate here, and if I provide the input, so here we need A bar C B bar. Okay, so if I provide the input as A, sorry, A bar C B, not B bar, A C bar B bar, then the output here will be A plus C bar plus B bar whole complement. Okay, and that is equal to A bar C B. Okay, so this is the implementation of the function using two NOR gates. Okay, so in the next series of the question I will try to keep more difficult questions which are more expected in the gate exam, related to minimization of gate, the number of NAND and NOR gates required to implement a function. So I will keep such questions in the next Tuesday session of the digital electronics. Okay, so thank you students. Keep sharing these lectures. It will help you to cover the syllabus for the exam in a more religious and a more systematic manner. Okay, so thank you.